So let's now focus on the continuous phase transition. Before I put this up, and I want just to say that the loop representation, it also works when you take more specific, other boundary conditions. So you remember I mentioned the Dobrushin boundary conditions. So what were there? You take a domain, and you take 2 points on the boundary. Here it will be this guy, and the one that I'm never going to reach there. And what you do is that, if you take a nice domain, so simply connected, what you will have is that you have two arcs which are naturally defined on this by these 2 points on the boundary. Okay, one arc going from A to B, one arc going from B to A. And what you do is you take the boundary conditions which are wired on one of the arcs and free on the other one. So basically, it just boils down to say that on one arc, you open automatically all the edges. And on the other arc, you take the dual arc and you open the dual edges. Okay, that boils down to that. So think of boundary condition like that. And now draw the configuration omega and its dual, and draw the loop representation associated to it. What happens is that you will have loops, but you will also see one interface which is leaving from this point, and the only way it can stop is reaching the other point there. So you have one interface and loops. So I told you this Dobrushin boundary condition, they are often described by physicists as being domain wall boundary condition, which I think is a much better name. Why? Because you have a wall, you have an interface, which is automatically selected by the boundary conditions. So this interface, I will call it gamma. Okay, very good. So maybe I don't need that for some time, so I'm going to just remove it to be able to write on the board. Okay, so now the continuous phase transition. The continuous regime. So we are going to have to introduce a new tool in order to understand this phase. And this is a very useful tool, which was first introduced by Kadanoff in the early 80s and then rediscovered by several people. But let's say that it was mastered by Stas Smirnov a few years ago to prove that you have exponential, that you have conformal invariance for Q equal 2. So this is third section, continuity for Q smaller or equal to 4. And so I will tell you about this new tool. So you have your path gamma. So you take Dobrushin boundary condition. So remember I said that I will write it like that. A, B, and then I take PC, Q, and omega. Okay, that's the measure with Dobrushin boundary condition on omega, where the two selected points are A and B. And when I do that, and I look at omega bar, there is a path, gamma, which is gamma of omega, which is the exploration path that I described before. So this exploration path is defined on the medial lattice, right? So for an edge, E of the medial lattice, so let's say omega of the medial graph, omega diamond, you can define the winding of the curve gamma at E to be what? To be the number it's going to be pi over 2 times the number of right minus number of left turns that the curve does between E and the end. Okay? So it turns left, right, and so on. You count the number of right turns. You subtract the number of left turns, and you multiply by pi over 2. It's a total rotation in radian between the point E, the edge E, and the last edge. Okay, so this is just a definition. Do you need examples, or is it clear for everybody what it is? Maybe I should give examples. So if you start like that, and you do something like that, here you can check that the number of left turns minus number of right turns is going to be 0. So the winding is going to be 0. But maybe you do something like that. And then it's going to be minus 2 pi because you did 4 left turns more than right turns, and so on. Okay, you have different types. Sometimes you start like that, you end up like that. It gives you, for instance, minus pi over 2. Okay? So the definition is the following. For p in 0, 1, q bigger than 0, and omega AB a Dobryshin domain, then for every edge in the medial lattice, in the edges of the medial lattice, maybe here I should have written it like that, you define the observable at E, which is something that depends on E, P, Q, omega, A, and B, to be the following. It's almost the probability. It's almost the probability that the edge E is on the exploration path. Except that you twist it somehow. You add a e to the I sigma times the winding of the curve gamma between E and the end. And there is one thing that I introduced here, which is sigma. So I need to tell you what it is, where sine of sigma pi over 2 is going to be equal to square root of q over 2. You're going to see why you want this. Don't worry. It's not so mysterious. So this is the observable that we will call the parafermionic observable. So F is called the parafermionic observable. Why parafermionic observable? This sigma, I mean, if you notice for Q smaller than 4, well, sigma is just a real number between 0 and 1. And this sigma has an interpretation, in this case, of a spin. If you think about it, for Q equal 2, sigma is equal to 1/2. Okay, sine of pi over 4 equals square root 2 over 2. And in this case, the model is related to the Ising model, which is a well-known model, fermionic model. So, I mean, there are many quantities that you can compute in terms of fermion in this model. So here, the sigma seems to match the interpretation of a spin. Same thing for Q equals 0. In fact, the model is related to the uniform spanning tree, which is related to dimers and things like that, which is a bosonic. And you get sigma equal 1 in this case. So you recover again the interpretation of a fermion. Oh, sigma equals 0, maybe, sorry. So that's why we call it a parafermionic, because for other value of sigma, well, since they are not half integers of, yeah?
Stupid question. I don't see what is the role of E in the definition of W gamma of E? The number of right turns and left turns of gamma.
Yes, but between the edge E and the last thing. So E is an edge of your medial graph. In gamma, yes. Otherwise, so otherwise you put 0. Yeah, otherwise put 0. Because basically, since you put the indicator here, no, you're right. Yes, you're right. Ooh, oh. Generation of French mathematicians are upset at me right now. Indeed, it was not defined properly. I acknowledge that. Former professors, you need to be very careful, you know. You didn't taught me like that, I know. Just I took liberties from there. So, indeed. For Q smaller or equal to 4, so then, yes, if sigma is not equal to 1/2 or to 1, there is no interpretation in terms of, there are no particles that have this fermion, or I mean this spin. But I mean, they are called parafermionic in this case, and they still have an interest as objects, I mean, hypothetical objects. hypothetical objects. So for q smaller or equal to 4, sigma is between 0 and 1. And for q strictly bigger than 4, in this context, what you get is, well, sigma is not real anymore. Sigma is going to belong to 1 plus I times r. Okay? And there is no physical interpretation of this sigma. But you see that already there is something happening at 4 as well. So it matches a little bit Baxter's conjecture. There is something different for q smaller or equal to 4 and for q strictly bigger than 4. So we will try to go further that way. I mean, to understand this connection better. Very well. I mean, a priori, if you think about it, the gamma is, so it's this exploration path is the interface between the primal cluster connected to the primal arc, to this arc where I said everything is wired, and the dual cluster connected to the dual arc. So it's really an interface like that. So this seems to tell you a lot about the geometry of your model. If you can understand the geometry of this exploration path, you basically understand the geometry of a typical interface. Very good. So it would be very good if you can have just the probability that the edge is on your graph, on your exploration path. It will give you something about the distribution of this exploration path. So here we do something more complicated. We add this winding number. I mean, why do we do that? It seems more complicated. Well, we do that because there is some integrability property of this observable. It satisfies some local relations. And that's the following that I want to highlight. So for P equal PC, what do we get? We get that if you look at the following quantity, the sum, so imagine you take a sequence of let's assume you take a sequence of vertices of the medial graph, of the dual of the medial graph. So this is the medial graph. No, sorry, the medial graph is rotated. And imagine you take vertices like that. So say V0, V1, V2, V3, etc. I want to define somehow the discrete version of an integral along this contour. So how do I do that? Well, I'm going to just write that it's a sum for I equals 0 to k if I have k minus 1, if I have k vertices, of vi plus 1 minus vi times f of the observable. So I do v2 minus v1 times the value of the observable here. v3 minus v2 times the value of the observable here. So I'm going to define the value of the observable on the dual edge of the edge vi plus 1. So this somehow is what? It's a definition of the integral along the contour, let's call it C, of f of e dE. So this is the contour C. Do you agree that this is a natural definition of a discrete contour of this observable? Well, for P equal PC, this thing equals 0, whatever the contour. So this is somehow, if you think of this observable, there are two ways of looking at this thing. Maybe the most intuitive one, but which is also the wrong one, which is CF as a function, a discrete function. Well, this is saying that the discrete contour integral equals 0, so this is suggesting that you have something like a discrete holomorphicity. You know, remember Morera theorem? Well, you have a continuous function whose contour integral vanish. It's an holomorphic function. So here, seems to be the discrete version of that. Well, that's a little bit, that's not the right way of looking at it, because in terms of discretization, if you want to define the observable, this observable is defined on edges, so a more natural way of looking at it is to look at it as a form, a discrete form. And then it just becomes the fact that this form is closed. So this is not sufficient to say that it's holomorphic. Somehow you will need it also to be curl-free. So anyway, this is kind of a glimpse of discrete holomorphicity, and this is really at PC. Very specific property of PC. So what do we do with that? No, first we prove that, sorry. So let's try to prove that. And the first thing we are going to notice is that since omega is a simply connected domain, since there are no holes in it, it's sufficient to prove this property for just one, so if I do like that, for just one discrete contour like that. If I do it for any of these discrete contours, then I can just sum exactly over all the small square inside, and I will get that the discrete contour vanish. Okay? So let's say that this is edge A, no, A and B, C and D. Okay, so I want to prove, let's say that f of A, I'm going to write it as a sum of the A of omega. So what is that? This is a contribution of the configuration omega to F. So it's basically e to the I sigma winding of E in gamma, indicators that E is in gamma of omega, times the probability at PC of omega. Okay? This is the contribution of the configuration omega to F. So what I need to prove, if I want to prove that this discrete contour vanishes, I need to prove that the sum of the omega of C omega minus A of omega is equal to the sum of, I times the sum of the omega. Maybe I should put the I on this side. Times the sum of the omega of B of omega minus D of omega. If you think about it, that's exactly saying this thing, this discrete contour equals 0. So it's a huge sum, and I want to get the cancellation between these two things. So it's, I need to get the equality between this. So a priori, it's difficult to do, right? There are many, many things. But what we are going to do is that, if I want this huge sum to be equal to 0, maybe it's sufficient to pack configuration together in such a way that already just for these configurations, I have cancellation. The best thing would be, imagine maybe for every configuration omega, I times this thing is equal to this thing. Then, of course, if you sum over every configuration, it's going to be true. So it's not true that it vanishes so easily, but somehow it's almost true. In the sense that, imagine, so you are here. Let's say that this is primal and this is dual. Everything is symmetric. You can do the other way around as well. So you have an edge which is either open or closed, right? Take S to be the transformation that goes from a configuration omega with this thing to the configuration omega with this one. So it doesn't move anything, it just switch the state of the edge from open to close. So it's an involution. Well, what we are going to prove is simply that I times C of omega plus C of S of omega minus A of omega minus A of S of omega is equal to B of omega plus B of S of omega minus D of omega minus D of S of omega. So it's not true that for omega alone the 4 terms vanish, but it's almost true because you just take the, it's not almost true, but it's not much more complicated to see, you can just group omega with the switch of omega, and you get that then these 8 terms vanish. Okay? So you agree that it's sufficient. Since it's an evolution, if I prove that, I'm done. So I need to convince you of that. So first thing, imagine that, so we are at the vertex, we are at this edge. Imagine that gamma doesn't go through any of the 4 edges. So imagine omega, gamma of omega doesn't visit A, B, C, or D. Okay, so the guy is getting like that. So here means that you have either one loop or 2 loops going through this guy. But switching the state of the edge is not going to change the fact that this path gamma is never going to get there. So in this context, all the contributions are 0, simply. Okay? So of course, there is equality. So I can restrict myself to the case where the path gamma goes through at least one of the edges. And let's just say it goes through A. Okay, that's, I mean, it's going to be, everything is symmetric. So let's say it goes like that. So it goes through A. So now there are two possibilities. Either it goes like that, or it goes like that. I mean, let's say, okay, it enters through A, and let's assume it goes out through D. I mean, if it goes out through B, you do the same thing the other way. But let's say if it goes through A and then exits last through D, there are two possibilities. Either it visits the 4 vertices, or it visits only 2, and there is a loop. And notice that these two things are mapped to each other through by the configuration, by the involution S. Okay? If this was, say, open, when I close it, I need to turn the other way, and I get a loop, and vice versa. Okay? So I'm going to assume I'm going to assume this is omega, and this is S of omega. And now let's try to see what are the contributions of omega and S of omega. I'm going to all express them in terms of A of omega. So let's call this X. Okay, so let's call X is by definition, or maybe just let's call it A of omega. I don't know why. A of omega. So here, so you have A, B, C, and D. What is the contribution of B? Well, the path doesn't go through it, it's 0. What is the contribution of C? The path doesn't go through it, it's 0. What is the contribution of D? Well, first, the probability is the same for A, for B. This is 1. So there is only the winding which is changing. Okay? Well, the winding at A, we do one additional right turn that at D to go to infinity. So the winding here is going to be e to the minus I sigma pi over 2 times A of omega, because I have one right term less to end up, right? Now here, S of omega. What is the winding of the curve? How did it change? Well, instead of doing one right turn, I did one left turn and 2 right turns. I mean, one left turn. No, two left turns and 3 right turns. Or maybe it's 3 left turns, but then I would have done 4 right turns, and so on. So the winding is exactly the same as here. The indicator is 1 still, but now the probability changed a little bit. Why? Because now I have one less loop. So here I'm going to get A of omega divided by square root of Q. This is the contribution of S of omega to this sum. B. Well, B, I do one left turn less than before, so I'm going to get e to the I sigma pi over 2 A of omega divided by square root Q. Here for C, you can compute that you are going to get e to the I minus I sigma pi A of omega over square root Q. And the last one is going to be this one. So, I mean, just you can compute it at home. I mean, it's not, there is nothing hidden there. But now you need to do this plus this minus this, multiplied by I, and compared to this plus this minus this. And what happens is that if you assume that e to the I sigma pi over 2 minus e to the minus I sigma pi over 2 is equal to square root Q times I, you get that all this thing vanishes. So you tune sigma in such a way that all this thing vanishes. And one of the main points was that everything is expressed in terms of A of omega. So you can factorize by A of omega. So it doesn't depend on the configuration, where it is, or so on. There's just one equation which allows to make all this type of quantity vanish. So to make this always equal to 0. Okay? Well, that's a proof. That's a beautiful proof. So it was rediscovered by Smirnov. In fact, I mean, it happens to be present in a paper by Bertrand Hénard in another context on quantum groups in the early 90s. But he didn't see what you can do with it, basically. Or he did something else with it. That's a more accurate thing. OK. So now we are basically ready to try to prove our theorem. So theorem, which is due to myself, Sidoravicius, and Tassio. I mean, yeah, let's say like that. And which says we are going to prove that for Q smaller or equal to 4, the phase transition is continuous, and we are going to basically, we are just going to prove that the third property, the fact that the sum for x in Z2 of phi 0 PCQ of 0 connected to x is infinite. That's the property we are going to prove. So that was one of the weakest. In fact, what I'm going to do is I'm going to only prove this for Q smaller or equal to 2 formally. I'm going to explain for 3 that, I mean, for 3 there is no additional difficulty. Between 3 and 4 there is an additional difficulty, and you need to prove slightly more than that. You are just, I mean, slightly less than that. You are going to prove that just it doesn't decay exponentially fast. But this, we prove that it was equivalent anyway. OK. Well, picture. So what do we do? So let's focus on the case 1 smaller than Q smaller than 2. And let's look at, so we know that discrete contour integral vanish. So let's try to find a good geometry where we can extract information from this property. And the nice geometry is going to be the following. Take this domain. So what is this domain? It's basically the domain minus nn times 0, minus n0. Okay, you take this domain. So what I did here, I did something slightly different. I rotated the lattice by pi over 4. Okay? So then now the original lattice is that direction, and the medial lattice is really a square lattice. Just for convenience, there is nothing deep there. And so you look at this domain, and let's just take as a contour the exterior of the domain. Okay? Take the boundary of the domain. And you just write, well, the integral of f of e dE equals 0. So what does it give us? So that's the first time in my life that I'm going faster than I expected. So I'm going to slow down even more. So the integral of this thing equals 0. If you think about it, it gives you that the sum over the edges at the top of f of e is equal to the sum over edges which are not at the top of f of e. And here I have a e star, which is basically, I mean, this is a vi minus vi plus 1, or it's maybe minus e star, whatever. It's not going to be so important. So I have the sum over these edges that are crossed by my path. And at the top, since I'm going like that, the factor vi plus 1 minus vi is just 1 in this case. OK. So let's look at this part. So first, there are the two edges. There are the two edges that are surrounding 0. OK? So you have 0, you have the face like that, and you have one edge going in and one edge going out. So I should have said something. if I use, I mean, here when I say that I use the observable, I need to tell you the boundary conditions. I didn't tell you the boundary conditions, right? So I'm going to take the free boundary conditions. But you can see the free boundary conditions are simply Dobrushin boundary conditions with A equal B equals 0. So you just wired the arc AB, which is just 0. So in this context, what is the exploration path? Well, the exploration path is simply the loop going around 0. So you have your boundary and you have a loop which is going like that. This is my exploration path gamma of omega. It starts there and ends up here. Okay? Maybe I'm doing it in the wrong direction. Well, that's not important for the understanding. So now, what is the contribution of this edge? Well, this edge is necessarily on the loop. There is no choice. And the winding, so the indicator is 1. And the winding, well, the winding is always 0 because I'm looking at the winding from this edge to this edge. So this edge is always contributing 1 to the sum on the left there. So I get 1. Now, the other edge, this edge, well, it's always also on the loop. There is no question about it. But now the winding is going to be always pi. I need to do 2 right turns. So this guy is contributing to the sum by e to the I sigma pi. Now I have the sum over all the other edges at the top. And what I'm going to do, I'm going to divide them in 2. I'm going to associate them by a group of 4. So I look at an edge, at a vertex x. I look at the 2 edges around this vertex. And I look at the vertex minus x. And I also look at the 2 edges related to, surrounding this face. Okay? So for every x on the left, on the right, say, so for every x, now it's a vertex on the right, I look at the contribution of the 4 edges. So what is the contribution of, say, this edge? If this edge is on the path, is on the loop like that, what does it mean? Okay, what did I do? Like that. Yes. Ah, thank you. Now I feel better because the orientation was wrong. So if this edge is on the path, thank you, what does it mean? Well, it exactly means, you can check, that there is a path of open edges going from there to there. So it means that 0 and x are connected. Now, so that means that the absolute value of f of e is going to be just the probability that 0 and x are connected. Now the winding, well, the winding of this edge, to go to this edge, you can check, you need to do 4 turns on your right. So the winding, and whatever the realization of this loop. So the winding of this edge, the contribution of this edge is going to be e to the I 2 pi sigma times phi pc q0. So let's call this Rn of 0 connected to x. This is the contribution of this edge. Now the contribution of this edge here, well, same thing. If the edge goes through this thing, means that 0 and x are connected. But now I only need to do 2 turns on my left. So I'm going to get a winding, which this time is e to the I pi sigma. You can do the same on the left. You're going to check that this guy is going to have winding 0 and this guy winding minus pi. So I get these contributions. So you notice that if you multiply everything by I to the minus I sigma, so if you multiply all of this by e to the minus I sigma pi over 2, what do you get? You get twice the cos of pi sigma over 2 plus sinus of 2 pi sigma divided by sinus of pi over 2 sigma times the sum for x on the right of phi pc q rn 0 of 0 connected to x. And you notice that for sigma between 0, for sigma between 0 and 1/2, well, this quantity is always, this is positive. So this quantity is always going to be larger or equal to twice the cos of pi sigma over 2. So it's never small, this part. So this is good because it's telling me that this part in absolute value is not too small either. But this part, exactly like I did here, if I look at the absolute value of f of e, I'm going to get the probability that e belongs to the path, and this probability is exactly the probability that 0 is connected to x. And for every vertex here, I have exactly 2 guys associated to this vertex. So this thing is going to, when I take the absolute value here, so I will get that twice the cos of pi sigma over 2 is smaller or equal to twice the sum for x not on the top of phi 0 pc q at 0 connected to x and rn. So the expected number of points on the boundary connected to 0 is always larger or equal to twice the cosinus of pi sigma over 2. That's very good, because now what do you do? Well, by comparison between boundary conditions, you can just remove the Rn here and say I am in infinite volume. I'm only making things bigger. And here, instead of x not on the top, I can just say x on the boundary of the box of size n, because that's exactly where they are. So I'm just getting that the expected number of points at distance exactly n connected to 0 is larger or equal to something which is strictly positive and which doesn't depend on n. If I sum on n, on the right I'm going to get the expected number of points connected to 0. On the left I'm summing something positive, I'm going to get infinity. That's finished. So this works very well for q between 1 and 2. What did I use? Well, I use really the fact that this thing here is positive, because as soon as this thing becomes negative, a priori this could cancel out this part. And there is no reason it doesn't. And in fact, it does. So what is going to happen is that you cannot even hope, in fact, for q between 2 and 3, you cannot hope that this quantity doesn't go to 0, in fact. It's going to go to 0. You can do a small computation and see that it goes algebraically fast to 0. So that means we cannot work in this geometry somehow. But what you can do is that you can see somehow why is it going to be, why cannot you hope that this is going to remain bounded away from 0? Because if you think, and this is just hand waving, okay, but if you think at the probability that x is connected to 0 in this geometry, you need a path getting to distance n here and a path getting to distance n here. So this, probability of having a path to distance n, you saw that it decays polynomially fast. That was, at least if you assume that the phase transition is continuous. So this thing is going to decay like 1 over n to a certain exponent that I will call alpha of q and pi. And I need this event twice, so it's going to decay like that. 1 over n to the 2 alpha q pi. This is an exponent. Okay, I don't want to give you exactly what is the value of this exponent. Maybe I can actually get rid of that. as soon as alpha q pi times 2 is bigger than 1, well, even if I have n points on the boundary, this thing is never going to be larger than a constant. So this thing is going to tend to 0. Okay? Well, in fact, alpha q pi is bigger than 1/2 if and only if, I mean, the prediction, if and only if q is larger than 2. So really, there is no hope you can make this thing work in general. But now you expect, when you have a continuous phase transition, you expect also that you have conformal invariance. And if you have conformal invariance and you look at the same event, but you look at this kind of geometry, and you want this guy to be connected to distance n and to distance n, here you are going to pay a 1/n to the alpha q pi. But here the exponent that you are going to pay is going to be a little bit better. It's going to be alpha of q 2 pi. It's a different exponent. In fact, it's twice smaller than this one. So now you only need alpha q pi to be bigger than 2/3 instead of 1/2. And this, it works up to q equals 3. But you are still not up to q equals 4. But why stopping in such good way? What you can do is try to open even more, so get to something where you are going to work on a universal cover. And in this context, you can see that you can work on a universal cover that opens a certain number of times, and you will only, for every q smaller than 4, you will be, in fact, able to find a big enough opening that this exponent is going to be smaller than 1, and that the argument I made here, I mean, you will be able to apply it to this strange geometry where you are working on this universal cover. Because in fact, this alpha q pi tends to 1 when q tends to 4, so for any q smaller than 4, you can find an opening big enough that this is going to be smaller or equal to 1. So I don't want to go in more details there because, I mean, it will take too much time. But the philosophy of the argument is the same as for q between 1 and 2, except that you work in a brighter geometry somehow. You open a little bit, you give a little bit more space for your path. Okay, so this is how you prove the theorem. So for q between 1 and 2, you have a proof. I mean, I didn't hide anything. For q between 2 and 4, well, you need a little bit. You need to work a little bit more because, in particular, if as soon as you are above 3, you cannot just use a comparison between boundary conditions because now you are already on something which is non-planar anymore. It's kind of a discrete Riemann surface. So you need to work more to be able to bootstrap the information you got on this universal cover to the plane. But you can do it, and it works. Let me finish. I have 10 minutes. Let me finish by giving you a new proof. And somehow it's funny because, well, OK, it's going to be a new proof of PC equals square root of q over 1 plus square root of q. Let's say for q between 1 and 2. Works for q between 1 and 4, but I'm going to only present it for q between 1 and 2. And I want to present this proof because it's very much people who saw the proof of percolation on the first day are going to recognize the same strategy. And in fact, the funny part is that, I mean, this is the first proof. It's not percolation. This is how we got to the percolation proof that some of you heard about. And by complete randomness, somehow, we were discussing, I mean, Vincent Tassion was telling me about an argument on about something completely different, and somehow it rang a bell that because I wanted for a long time to prove PC equals square root of q over 1 plus square root of q using the observable, and it rang a bell that, oh, we can do it now, and that's the argument I'm going to present to you. And then we realized that, in fact, the argument was working super well for percolation in any dimension and so on, and also for the Ising model. So it's funny that somehow just trying to reprove all the old theorems. I mean, we were not heading for it at all. Like, it was just pure randomness. But anyway. OK, so let's prove theorem that for 1 smaller than q smaller than 2, PC of Q is square root of Q over 1 plus square root of Q. So I apologize in advance for people who didn't see the proof on the first day. It's going to be maybe a little bit tougher for you to follow. But since I have 10 minutes, I will try to almost give it full. So remember that for percolation, you have Rousseau's formula, which is telling you that the derivative of the probability of an event, whatever the event you choose. So let's say, for instance, 0 connected to the boundary of the box of size n. Well, for Bernoulli percolation, this is equal to the expected number of pivotal points. So the pivotal points, for those that were not there on the first day, is the edges that if you, an edge is pivotal for a configuration omega, if when you open it, your configuration is in the event, and if you close it, it's not in the event. Okay? So it's an edge, it's a decider somehow. So for Bernoulli percolation, you have that the derivative is exactly equal to the expected number of pivotals. And if you think about it, then being pivotal doesn't depend on the state of the edge, because whatever the edge for the configuration omega, anyway, you are saying, if I open it, it's in it. If I close it, it's not in the event. So it doesn't depend. So it's also equal to 1 over 1 minus p times the expected number of closed pivotals. Well, for random cluster model, it's almost the same, except it's an inequality. So you have larger or equal to a constant, whatever, it's not 1 over 1 minus p, but it's a very explicit constant, times the sum over the edges in my box of the probability that E is pivotal, the edge is pivotal for the event 0 connected to the boundary of the box. So this is exactly saying, so being pivotal for this edge is exactly saying the following. It's saying, so this edge, let's call it xy, is pivotal if when it's open, there is a path from 0 to the boundary, but when it's closed, there isn't. So that means that when this edge is closed, there is a dual path blocking 0 from the boundary of the box. Okay, so this is typically what you will see. That's what it means to be pivotal. Okay, and I'm asking that it's a close is pivotal and E is closed. Sorry. So I'm asking that the guy is also closed. So this is the configuration. You are summing over the edges the probability of this thing. So let's now define capital S, round S, sorry, to be the set of vertices in lambda n which are not connected to the boundary of the box. Okay? And let's just decompose this sum. So let's forget about the constant. Okay, let's assume there is no constant here. That doesn't change a thing. Let's decompose this sum according to the possible realization of S. So I look at the guys that are not connected to the boundary. I look at the possible realization of this guy. So it's going to be the sum over S of the sum over E in E of lambda n of phi p q of E closed pivotal for 0 connected to lambda n, and S is equal to S. So I'm somehow conditioning on the set of vertices which are not connected to the boundary. Now imagine let's forget about that. Imagine this is the set of vertices connected to the boundary. And this is the set of vertices not connected to the boundary. Where are the pivotals? Who are the pivotal vertices in this case? Well, they are exactly all the points on the boundary of this surface which are connected to 0. Because these guys are in such a way that if I open, I'm going to have a path from 0 to the boundary. If I close, I'm not going to have it. So this thing, if I look at it, so it's the sum over S. And if, say, I condition on S equal S, then the expected number of pivotals is what? Is just the sum over X in in the boundary of my S of the probability that X is connected to 0. So if I want this guy to be pivotal, what do I need once I condition on S? I just need this guy to be connected to 0. Okay? But the domain Markov property is telling me that conditioning on everything else outside, the law of what is inside is going to be a random cluster model in this graph with boundary condition induced by what is outside. But since what is outside is not connected to inside by definition, because inside is the points that are not connected to the boundary, outside it's the points that are connected to the boundary, you have free boundary conditions. So this is, I mean, once again, there was exactly this proof for Bernoulli percolation. It was simpler in this context. Here it's a little bit more difficult. But for those who saw it, you see that it looks a little bit the same. The big difference is that for Bernoulli percolation, you can just use independence. You can just say what is inside is independent of what is outside. Just completely independent, Bernoulli percolation. Here it's not that, because inside you can I mean, it is dependent of what is outside, but only through the boundary condition, and the boundary conditions are the free boundary conditions. So you get something like that. Now, what was the argument for Bernoulli percolation? The argument was for P larger than, say, for instance, square root of Q over 1 plus square root of Q. I mean, if I would do it in dimension 2, this thing is larger than 1. So this implies that the derivative is larger than the sum of this quantity. And the sum of this quantity, so the derivative, is going to be larger than the sum over S of the probability of S equal S. And this was 1 minus the probability of 0 connected to the boundary. But now you see, as soon as you have this type of inequality, it implies that when you increase P, the derivative has to be positive. So it tells you, this tells you that this guy this guy is larger than something like 1 over P times P minus square root of Q over 1 plus square root of Q. So if you have this larger than 1, for any P larger than square root of Q over 1 plus square root of Q, you get this inequality. And now when you let n goes to infinity, you get the probability that 0 is connected to infinity is larger than it's strictly positive. So this will tell you that PC has to be smaller or equal to square root over 1 plus square root of Q. And remember that Zhang's argument, the one which is easy, gives you that PC is larger or equal to square root of Q over 1 plus square root of Q. So the only thing you need to understand is why you have that this quantity is larger or equal than 1 or than a constant, because here you could add a constant, it's okay, for P larger or equal to square root of Q over 1 plus square root of Q, right? So for instance, why it's larger than a constant at PC, at square root of Q over 1 plus square root of Q. And how do you do that? Well, this is exactly the expected number of points on the boundary connected to 0. Well, do exactly like before. Look at the domain, look at S. So let's say S is this guy. Take 0 and just draw a line like that and look at this domain. And do exactly the proof that we did for the domain Rn. Do exactly the same proof. What is going to happen? The expected number of points connected like that on the top here is going to be, I mean, with the constant in front is going to be positive. So it's going to tell you that the expected number of points here connected to there is larger or equal to twice the cos of pi sigma over 2. Uniformly in the shape of S. Whatever the shape of S, you will have that. And this is exactly what you are going to inject there to do this thing. So in fact, the argument for percolation, I'm sorry, the argument for the random cluster is a little bit more obscure somehow, but it's really from there that we got the argument for percolation, which this argument is not restricted to planar case. It's not restricted even to percolation. You can do it for the Ising model and so on and so on. But it came from this argument, from this observation that this quantity somehow was much more natural to me in the random cluster context because I knew about this type. I was trying to prove things using this type of idea, except that I was missing somehow this differential inequality, which was so simple, but was still eluding me. Okay, so we see each other, I hope, on Friday. Thank you very much.